We're here today to review polynomial functions and, generally speaking, how to graph them. So let's get started. First off, polynomial functions take on a variety of different forms. They can be linear or they can be nonlinear, and this one is cubic. And we normally classify polynomials by their highest degree. In this case, the highest degree is 1, which is why the first example is linear. In the second example, the highest degree is 3, as evidenced by the exponent, so this would be considered cubic. And the end behavior, or the graph's behavior at the extreme ends, the left and the right side, is determined by the leading term, or that most powerful term. Now, the most powerful term is normally it normally has an exponent, right? Well, it'll always have an exponent. Even in linear, this exponent would be a 1. And it will normally have, or will always have, a coefficient. Whatever that coefficient and exponent combination are will determine whether your graph goes up and then up, down and then down, or some variety of those two things. Let me give you an example. Let's imagine that we have an equation that says y equals 3x squared plus something. We don't really care about the something plus something after it because we only care about the most powerful leading term if we're writing them in the correct order. So let's go ahead and focus on the 3x squared. If I use my chart, the a value, 3, is positive. So I'm looking in this column right here, this row right here. And the exponent is 2, which is even. So I'm looking in this column right here, and you can see that the place in which they overlap is going to be up, which means my graph is going to be going up on the left end. It'll do some stuff in here. We don't really know what yet. And then it'll come up again on the other end of the graph. Now, as we go through this review, we're going to try to figure out what's going on in between. But for our leading example, all we can determine right off the bat is what the end behavior of our graph is. And you have 4 choices. And it has to be one of those choices. All right, so let's go ahead and check it out. I want you to try this one. And that is down, up. Now try this one. This one is down, down. It's down, down because we know they're going to go the same direction, and negative means opposite. So negative is down, down. And one more. This one should be up, down. All right? It's opposites because they're odd, and it goes opposite of the original, right? Down, up was the positive version, so up, down is the negative version. Okay, moving on. Turning points. Turning points are defined as spots where our graph stops going up and begins going down, or stops going down and begins going up. It's some sort of curve to the graph. Turning points are generally described using the most powerful term. And what you do is you take the exponent of that most powerful term, you take 1 less than it. So if I have x to the third, I'm going to do 3 minus 1 and get 2. And then I'm going to list all of the 2's, or I guess minus 2's, down to 0. So 2 or 2 minus 2 is 0. So something with an x to the third power will have either 2 turning points or no turning points. If we try this again for the one below it, x to the fourth, this one, 4 minus 1 is 3, so I'm going to have 3 turning points, or 3, take 2 off of there, and 1 turning point. So you have some options. This doesn't tell you what it's going to look like, it tells you what it could look like, and that might help you as you move along. Now let's move on from end behavior, which I think is very important, and turning points, which is marginally important, down to something that is back to really important again. Polynomials, their factors, and their zeros. Now, factoring a polynomial should not be new. The zero product property should not be new. The zero product property simply means if I have 2 or more items multiplied together to give you 0, then one or both of those answers, one or both of those pieces, this one or this one, has to equal 0. And you've known the zero product property since Algebra 1, so no big deal there. At least I hope not. Here is the zero product property in action. And by the way, over on the right-hand side here, the number of the degree of your polynomial is how many roots you will have. It might be a combination of real roots and imaginary roots, But we're not really going to worry about imaginaries just yet. So for right now, if you see a 3, if you see a 3 as your most powerful term, that means it has a degree of 3. That means we're going to have 3 roots. By the way, this one item already tells me that I'm going to have down-up behavior. It tells me that I'm either going to have 2 or no turning points, and it tells me that I'm going to have 3 roots. So I get a lot of information from that very first piece. Now, what else can I do with it? Well, let's go ahead and change out the y for a 0. And if I swap out the y for the 0, we can factor. And now that we're factored, we can go ahead and identify that this is going to have 3 roots, just like predicted. The first root is x equals 0. The second root is x equals 4. And the third root, let's just be clear, is x plus 3 equals 0, so minus 3 to both sides. This is how you do it, is negative 3. So we have our 3 roots, 0, 4, negative 3. So our graph is going to go through the x-axis 3 different times. That probably indicates that we're going to have 2 turning points because our graph will probably come up, curve and go down, and then curve and go back up again, and our x-axis is probably going to look something like that. Now, to be more precise and to sketch this polynomial, if we were trying to sketch this particular one more accurately, a couple other things we would want to do. We would want to look for points in between our roots. So in between 0 and 4 are lots of numbers. We'd want to put some of those numbers back into the blue polynomial to see what happens. We'd want to find out what happens between 0 and negative 3. Again, lots of numbers in between 0 and negative 3. Let's pick one and put it back in and see what happens. When I mean see what happens, you're going to figure out some ordered pairs. The more ordered pairs, the more accurate your sketch. One or more of them might end up being a relative minimum or a relative maximum. Generally speaking, this point right here, whatever that would be a relative minimum. It's not the lowest point on the graph, but it's the lowest point on one of the turning points. And then this guy right here would be a relative maximum. To get your relative mins and maxes, we did some derivatives. We kind of played around with some pre-calc and calculus concepts. For this video, I'm going to say a good graphing calculator does a good job. Desmos will do a good job. Even just trial and error by choosing some additional points in between will get you pretty close to a relative min and max. Knowing end behavior is valuable, knowing turning points is valuable, and knowing, I wrote down bounces, but knowing your multiplicities is going to come in handy as well. Now, a multiplicity, you might recall, is just a repeated 0, and you could have more than one repeated 0. You could have 2 or 3 or more repeated values. If you have 2, the graph will be said to bounce. Now, I have an example here. Let's imagine that we have a factored form of something. Maybe we had y equals, and we factored the x side, and we got x minus 3 quantity squared. That means that x is 3 twice, right? Twice because there's 2 of them. That means that the graph is going to bounce off of x is 3. So let's imagine that if this is a 3 on my graph, if this is 2 and 1 and 0, our graph is either going to come up and bounce off of 3 and come back down, or our graph is going to come down and bounce and go back up. I kind of missed it there, but you can kind of use your imagination. That's what a bounce would look like. Now, bounces don't always look like that because if you have a different number of multiplicities, you might have some different impact. But for right now, again, Desmos, graphing calculator, following your turning points, you might recall that different multiplicities produce different images. But let's move on. So here is the process that I follow when graphing a polynomial by hand. I look for end behavior, turning points, roots, what the real roots actually are, if there's any multiplicities, and then the points in between. So let's try one together. I've moved outside for this second part of the video, so let's go ahead and sketch this thing. First and foremost, I notice end behavior. I see an exponent that is even. That means I'm going to be going the same direction, either up, up, or down, down. And I notice that my coefficient is positive. So up, up is going to be my end behavior. There's going to be, well, 1 less than 4, right? 1 less than the exponent of 4 is the number of turning points. So there's going to be 3 turning points, or there could be 1 turning point. The number of roots is going to be the highest degree. So there's going to be 4 roots. Could be real or imaginary or a combination. And here's where we start figuring out what the real roots are. To figure out the real roots, we take the equation portion, not the y, but the equation portion opposite of y, and we set this thing equal to 0. We're going to do some factoring. And once we're done factoring, we're going to use the zero product property. And there are 3 roots. What's interesting is that though there's only 3 that we're going to list, you'll notice that one of them has a multiplicity. This x squared equals 0. That squared on just the x means that there are 2 zeros. So while I'm only going to write 0, 3, and -2, I'll probably indicate that the 0 is a double. And the multiplicity is greater than 1. Yes, x equals 0 has a multiplicity of 2. All right, so that gives that. We recognize that when we graph that, we're going to bounce at x equals 0, and then points in between the roots. This is where we're going to go ahead and do a little xy table to kind of get ourselves sorted. So when x is 0, y is 0. When x is 3, y is 0. And when x is -2, y is 0, right? Those all come from my real roots. Here's the double, and then 3 and 4. That's our 4 roots. So we want to find out what happens in between 0 and 3, and what happens in between 0 and -2. So I'm simply going to use a calculator, and I'm simply going to do that calculation. One other kind of cool trick here, instead of putting it back into the original equation, I can put my new number into this factored form. And I'm going to pick 2 numbers. Any 2 numbers will do. Anything between 0 and 3 would work, so I'm going to pick 1.5. And anything between 0 and -2 would work, so I'm going to pick -1. We just want to know what's happening in between. So you'll see me fast forward and use the calculator to get this answer. There we have our table of values. 5 values should be enough to get us going. Points between the roots, we have 2 different points that we found. So let's graph these things. 0, 0, 3, 0, -2, 0. So 0, 0, 3, 0, -2, 0. And the 2 points we just found, 1/2 and -11.8. Now I rounded that off, of course, but -1/2 and 11.8 is probably about down here somewhere. And what was the other one? -1, -4 is here. Now, those just look like some disconnected dots, to be quite honest, but we also know a couple other things. We know our end of behavior is up, up, so we know our graph is going to go generally like this. We know that it could have a maximum of 3 or a minimum of 1 turning point. So let's find out how that works. And oh, by the way, we know that we're going to bounce off of 0 because we have a multiplicity of 2 when x equals 0. So let's see what happens. If I simply come down here, turn, bounce, turn again. Now my turn's going to be a little bit off, so let's redraw that. Turn again. And while I have to get rid of that piece and keep it going, I have 1, 2, 3 turning points. I have a bounce at x equals 0, and I have my 3 real roots. One of them kind of occurs twice. So this is our correct sketch of that polynomial.